today. We're going to do a little bit more population modeling with interacting species. Then we're going to talk about the harmonic oscillator some more. That, I haven't returned your exams yet because a few people still needed to take them. I did grade them, your scores on the roll. But I did notice the harmonic oscillator problem on the test was probably one of the more difficult ones, it seemed like, for people. Thought I explained the basics clear enough, but evidently not to people do well enough on the test for that one. So we'll talk about that some more. We'll also talk about what to do when there's friction involved, which is of course more realistic. In our book, the friction is called damping. It's sort of a general friction term. Talk about converting second-order scalar differential equations, one single second-order scalar differential equation, into a system of two first-order equations. The second-order equation comes from Newton's second law, and then we can convert to a system by defining the velocity to be the derivative of the position. And finally, today we'll consider what are called fully decoupled and partially decoupled linear systems, which are the simplest kinds of systems of equations that you could consider. All right, so let's go back to interacting species here. So far we've done predator-prey, but there's a couple other main models. Competing species and cooperating species. Take a look at these functions here. So these are going to be the right-hand side functions for a system of differential equations. dx dt is going to equal 3x times 1 minus x over 2 minus 5 times xy. So in the absence of y, when this term goes away, when y is 0, x grows according to a logistic model with a carrying capacity of 2. It's a negative coefficient in front of the x times y term. That's called the interaction term. It's negative coefficient. So the existence of y is bad in a sense for x's growth rate. It could cause x's growth rate to be negative. Similar kind of thing with the g function here, which would be from the dy dt equation. Logistic model in the absence of x, now with carrying capacity of 3, and a negative coefficient for the interaction term. This is a competing species model. These two species are competing for scarce resources because both of the interaction terms have negative coefficients. All right, in Mathematica, I define those functions like this. I define a new function that I call capital G. I could call it capital F here. Let's see, the other day I think I called it capital G because I had defined capital F to be something different. Capital G is the vector field whose components are little f and little g, written by hand. I will typically try to write it in column vector form. I might write g of xy equals f of xy in the first component and little g of xy in the second component. I will probably try to typically write it like that. But you should be comfortable with it if I don't. And again, the notation, the way we write the vectors, is not a real big deal. Don't make it too big a deal. We will typically find it more convenient to write it in column vector notation because ultimately in chapter 3, we're going to do some matrix multiplication for those in linear algebra. A matrix times a vector, and it will be more convenient if the vector is in column form. That's why we'll typically try to do that. But I might also do it like this. I might call this vector capital Y, like the book does, and I could write this as a row vector, or even as a point, and put a comma between them. However, again, when you graph it, you want to think of the outputs of this thing as being arrows. You want to think of them as being vectors. The inputs you should think of as being points for a vector field. At each point in the xy plane, at any given point, x comma y, you get a vector whose components are given by these two quantities here. Little f is the horizontal displacement. In this picture, that would be negative. I'm labeling it as a length, but it's a signed length. It's negative because it's moving to the left. And this one is a vertical displacement that's positive. That would be the value of g of xy at that point. And as you saw with this notation assignment, you vary the point, you get a different vector. Trying to draw the vector field means drawing a bunch of those vectors all at once. Hopefully, so the picture picture's not too messy. All right, so that is how you enter it in Mathematica over here. Does this have any equilibrium points? That's the first thing you should look for. You'd want to set these things equal to 0 and solve for x and y simultaneously, which you can do in Mathematica with solve. By hand, you want to factor. We've got 4 equilibrium points. The origin 0, 0. X equals 2, y equals 0, which should make sense since the carrying capacity of the x equation was 2. X equals 0, y equals 3, which should make sense because the carrying capacity of the y equation was 3. And then this other one that's harder to find, 8/19, 9/19, that's going to come about from factoring out an x out of this one and the y out of that one and setting the resulting linear equations equal to 0 simultaneously. I suppose it's worth writing on the board what that system would be in this example. Again, factor an x out of the first equation, multiply the 3 through, like this. Set that equal to 0. With a g function, factor the y out, and you get 1 minus, with a little rearranging, 2x minus 1/3 y. Actually, let's go ahead and solve this by hand with the elimination method. We did substitution before. Let's do elimination. This is like linear algebra here. I'm going to rewrite it in the following form. 3/2 x plus 5y equals 3. Just putting the 3/2 x and the 5y on the other side and flipping. Do the same kind of thing with this equation. 2x plus 1/3 y equals 1. How do you use elimination to solve this? You could, for example, multiply the top equation, say by, what would work well, 6 perhaps? Let's see. If we did that, the 2 cancels there, you get a net. Well, okay, let's see. What would be a good thing to multiply by here? I'm thinking about eliminating the x. I guess if I multiply this by 2/3, 4/3. If I multiply this by 4/3, 4/3 times 3/2 is 2. This would become a 2x. If I have to multiply everything by 4/3, if I multiply 5 by 4/3, I get 20/3. If I multiply 3 by 4/3, I get 4. Why did I do that? Leave the second equation the same. The reason I did that is because now if I subtract these equations, the x goes away. I've eliminated the x. Just double check things. So again, I was multiplying by 4/3. The 3's canceled. You have 2. 4 times 5 is 20. 20 over 3. 4/3 times 3 is 4. Now subtract. The x's go away. 20/3 minus 1/3 is 19/3. 4 minus 1 is 3. Solve that equation for y. It's easy to do. We've eliminated the x. Multiply both sides by 3/19. Y will be 9/19. Does that match Mathematica? Yes, it does. And then solve for x by plugging y equals 9/19 back into either one of these equations to solve for x. I'm not really doing the row operations completely like you do in linear algebra, where you try to get things into what's called reduced row echelon form, but it's good enough to get the answer. Okay, I'm not going to keep going here. I trust you can do it. Plug that back into here, say, and solve for x. I guess that's kind of a mixture of elimination and substitution. Next thing to do is to try to draw the phase plane. And by hand, you'd want to draw the way the phase plane looks on the axes by the fact that you've got logistic models in the absence of the other species. Then the hard part is using, well, trying to draw in the rest of the phase plane. For the moment, we're just using technology. So we use the VectorPlot and the StreamPlot. Combine them with show. I think I can just go ahead and type the G in here, actually. And we're going to stay in the first quadrant for the most part here. Don't want to go too far, maybe out to 5. StreamPlot is going to have similar syntax, except change the word vector to stream. I'm not worrying about decorating these things at the moment with various colors. Let's just see what we see. I probably should put colors in here. The straight arrows that are kind of long up here and barely seeable down in here, those are the vectors in the vector field scaled down. The arrows that kind of curve, those are the streams. Those are the solution curves. The solution curves follow the vector field. Let's go ahead and color it now to make it easier to see. And also use vector scale to make it really a direction field instead of a vector field because it looks nicer. Vector scale 0.03, none makes it work nice. So now all those vectors are the same length. Vector style, red, make them red. By the way, evidently with Mathematica 10, I just noticed this morning. Maybe you noticed it on the key yesterday. If I do thick red like this, it doesn't color them red. With Mathematica 9, that worked, the previous version. If you do double curly braces, though, you can make it work here. It's a change from Mathematica 9 to Mathematica 10 that I wasn't aware about until this morning. Let's just make it red and not thick. Stream style. Actually use blue instead of red, because I'm imagining this being a thin sheet of water. Imagine this plane being full of water, a thin sheet of water, and the water molecules are following the streamlines. Okay, is that literally going on? No, of course not. Could you imagine it going on that way? Like, are there real streams of water that are thin layers of fluid that do follow vector fields like this? Possibly. I'm not going to rule it out. I'm not going to worry about whether it's realistic or not. It's just a helpful imagination tool for us. We're pretending that the water molecules follow the streamlines. They follow the solution curves. More precisely, anytime one of these water molecules is at the location of the base of one of the vectors in the vector field, that vector field is a velocity vector for that water molecule at that moment in time. It's traveling in that direction, and the length of the vector in the vector field is the speed. Now again, this is a direction field. Those red arrows all have the same length, so we are losing the speed information, but it really is there. We just don't see it. We can see it if we add in some more. Let me get rid of the frame though first. Frame arrow false, axis arrow true. I'm putting those things in there. By the way, the axis should be labeled what? T? P? X and Y, yeah, okay. T is in the background. Time is in your imagination. You don't literally see the time in the picture. You have to imagine the solution curves, the trajectories moving as time goes by, indicating the values of X and Y are changing as time goes by. We can make our imagination more vivid by using Mathematica. We can use NDSolveValue. If I try to use just DSolveValue here, it's not going to be good enough. I haven't tried it actually, but I would bet money, if I were a betting person, but I'm not, that it doesn't work. DSolveValue, if I try to use that here, here's how I'd have to try to use it. I could even try to pick a particular initial condition, and as long as I don't pick my initial condition on the axes, it won't work, I'm pretty sure. Let's try x of 0 equals 1, y of 0 equals 2. Solve for x and y as functions of t. Bet it doesn't work. It's thinking, thinking, thinking. I think it's probably going to give up at some point. Well, we want to use, instead, I'll let it think for a bit here. What we want to use instead is NDSolveValue, putting a capital N in the front, causes Mathematica to do a numerical approximation to the solution, analogous to Euler's method, though better than Euler's method. My guess is it probably uses something called the Runge-Kutta method, which we don't get to in here. What is NDSolve doing? It's, again, doing a numerical method. It's computing a bunch of data points, essentially, a bunch of dots on an approximate solution curve, and then connecting the dots with some sort of interpolation method. Looks like DSolveValue is not even going to give up. It's just going to keep running here. So let's abort the evaluation. I could also quit the kernel. If you quit the kernel, it restarts Mathematica's memory from scratch. If you just abort the evaluation, it doesn't restart the memory. NDSolveValue does work. However, that's kind of strange output. This output is not really in a usable form as is. It's telling you that there's some stuff going on behind the scenes. There is a function. Oh, and I used it wrong here. I need an interval here. I noticed just a dot there. That's a problem. I need to let t start at 0 and go up to some positive time like 10. And then I get graphs here. And there's some interpolating function, again, unspecified behind the scenes. How can you make use of this? You could give it a name. You could call it, here's the traditional way to do it, x sol, comma, y sol inside curly braces like this. Set it equal to that. That will store this information in this list, whose first coordinate or first entry is x sol and whose second entry is y sol. The sol just is an abbreviation for solution. Once I've got that, I can put it into this picture inside the show with parametric plot. Solution curves to systems of equations are parametric curves. I can plot the entire thing by doing this. There it is. Not super exciting this time. Point 1, 2 is the initial condition. Evidently, the solution curve is going this way and up this way. Heading toward 0, 3, perhaps, which was an equilibrium point. Looks like 0, 3 might be some sort of sink. Let's animate it now, and let's also start our initial condition further away from 0. Why don't we start at the point 5, 2 instead? X equals 5. Y equals 2. Re-enter that. Put this inside of manipulate. Make the right endpoint of the interval here b instead of 10, and let b go from point 0, 0, 1 to 10. All right, now we see the curve move. And whoa, something different there happened. Cool. That was kind of cool. It didn't go up to 0, 3. It looks like it's going down to 0, 2. There's 2 sinks. And which sink you approach as time increases evidently depends on the initial condition you pick. Let's change it again. Let's make it 5, 3 and see if it does something different. Yeah, it does. Now it's going up to 0, 3. What about the speed information here? Do we see the speed? It's going very fast at first, and then it slows down. It's very fast at first. So fast you can barely see it on this time scale. Watch how fast it goes. Ready? 1, 2, 3, go. On that time scale, it practically instantaneously moved there. The vectors in the vector field are longer over here than they are over here. We don't see that, but that's what's the reality. So the speed is greater over here along the solution curve, and then it slows down as it comes up this way. You really should put the equilibrium points in the picture as well, with list plot, for example. I'm not going to take the time to do that right now. Before I put it on Moodle, I'll put the equilibrium points in it. What about a cooperating species model? I need to change my functions. Enter this code here, there's just 2 equilibrium points. This is cooperating species because the interaction terms have positive coefficients. There's no logistic model in the absence of the other species. They die off. In other words, they kind of need each other to live. Otherwise, they're going to die off. And we can do similar kinds of stuff as we did already. And it looks like we're going off to infinity there because we're getting step size of 0. I need to pick a different initial condition. Close to 0, for example. 0.1, 0.1. Then my solution curve does not go off to infinity. We better look in closer to the origin here, I think. Here's the picture. Oh, and well, my solution curve is not doing anything too exciting. It's just heading toward the origin. I guess they didn't, these were cooperating, right? Oh yeah, if it goes off to infinity, that's actually good. They cooperate and they benefit each other in making their growth rates really large and making their populations really grow as long as they are sufficiently large in population to begin with. But if you start off with a very low population, then they don't cooperate enough to benefit. They both die off. That makes sense? We're relying on the technology. In Chapter 5 especially, along with Chapter 3, we'll talk about techniques that will help us understand this and how you might even make it by hand to some degree. But right now we're relying on the technology. Actually, I think in class on Friday, I'll show you a little bit of how you can make it by hand.
Is the other equilibrium point a source then?
There's one right here. I think it's a saddle point. I think it looks like a saddle point. It looks like solutions are heading toward it in this direction and going away in this direction, and sort of going in a hyperbolic kind of way by it in other directions. It's right around here, it looks like, with the other equilibrium point.
Is that an node then?
It's called a saddle point. It's a higher dimensional node that kind of looks like a saddle point for multivariable calculus, and we call it a saddle point. All right. Let's go on to the harmonic oscillator now. Here's how you'd write the general equation in the form essentially F equals MA, or MA equals F, in the case where you allow some damping, some friction. Okay? In class so far, we considered the case where we only have Hooke's law to think about and no friction. I pretended there was no friction. You can approximate that if the mass is moving in a vacuum up and down and so there's no air resistance. There's going to be resistance from the spring itself, so there's always going to be damping. But maybe the internal friction of the spring itself is so small you could assume it's effectively zero and ignore the damping, ignore the friction. And just use Hooke's law saying the force is proportional to the displacement of the mass. Why is the displacement of the mass from equilibrium? K is the proportionality constant. Actually, negative K is the proportionality constant for that force. MA, mass times acceleration, equals the force. Now when we include damping, the damping we include looks like this. It's proportional to the velocity. And in this book, the constant of proportionality is called negative B. Is that the way friction really works? To tell you the truth, I'm not sure. As a first approximation for small oscillations, it seems reasonable. You would have to test the predictions of this model against experiment to know how good it is. Evidently, it's probably pretty good because otherwise we wouldn't use it. Okay, it is a common thing to teach this kind of model in physics. So that's the F equals MA form of the differential equation. It is a second order differential equation because you've got a second derivative there. You're after a function y as a function of t such that the mass times the second derivative of y is always equal to negative b times the first derivative minus k times the original function for all t. Again, there's t's in the background here. You don't see them except down here. We could use prime notation, and you should be fine with that. I could write this as m times y double prime equals negative b times y prime minus k times y, and then you wouldn't see any t's at all. But it would be understood that time is involved. Time is in the background, and y depends on t. We can rewrite it like this, putting everything that's non-zero on one side and 0 on the other side. We can also divide everything by m and write it like this. And that's probably the most convenient form to leave it in. Especially when you consider particular examples and you try to do some educated guessing about solutions. So let's consider one of those examples. I'm going to go ahead and use prime notation. Y double prime plus 7y prime plus 12y equals 0. Save some time to use prime notation. So we're after a function. Y is a function of t. I'm going to avoid calling it phi of t here. We will go back to phis later on, but not now. You should be okay with abusing notation like that. I could write y, I could write y of t, I could say they're equal. Technically, that's bad because I'm giving the same letter to the function name and the variable name. But it's the kind of thing we don't worry about in here. You're looking for a function whose second derivative plus 7 times its first derivative plus 12 times the function is always equal to 0 no matter what t is. Well, since this is a mass in a spring, it would be reasonable to guess something involving cosine, something involving sine. However, if you think about it, it's going to be hard to guess what would be a good combination of cosine and sine that might work. Like, what would the coefficient of t be? If you try a linear combination of cosine of something times t plus and sine of something times that same something times t. But it's hard to imagine what to guess here. It turns out it's better to guess e to some coefficient times t, where s is an undetermined coefficient. We're going to guess this type of solution. Now you might be saying, well, isn't that a bad idea because shouldn't there be some oscillation? And that kind of function is not going to oscillate. Yeah, that does seem like it might be a problem. However, you might also imagine if the damping, B, is large enough, maybe there's so much friction, like if the mass of a spring is moving inside gelatin or something, or lava, without burning up. Okay, maybe there's so much friction it doesn't oscillate. And maybe it's an exponential decay to 0. So if you think about it that way, maybe this is not such a bad guess. Turns out this is even a good guess when there is oscillation, however imaginary numbers come into play. And if you know about imaginary and complex numbers, you know that actually there's a relationship between exponential functions and trig functions, cosine and sine. So this is actually even a good guess when there is oscillation. Find its derivative. S is a constant. Use the chain rule. Find its second derivative. That's nice. Plug it into the left-hand side of the differential equation and see if there's some choice of S that will make it always equal to 0. And we will quickly see that there is. The left-hand side of the differential equation, upon substituting this function, becomes s squared e to the st plus 7s e to the st plus 12 e to the st. You want this to equal 0 for all t. Doesn't look at first glance like that's possible. How do you choose S so that that's always equal to 0? However, it is possible. How can I find a value or two of S that will make this work? This e to the st seems to be a complicating factor. How can you deal with that complication?
Factor it out.
Factor it out, yeah. You've got this equal to 0. It's useful to factor out whatever you can factor out. E to the st appears in every term. It can be factored out. If the product of two things is 0, then one of the two factors has to be 0. But wait, e to a power is never ever 0. I told you about the guy who, when I made that mistake once in grad school, right? He wrote, "What? Are you sleeping or are you crazy?" Something like that. E to a power is never ever 0. Again, some engineers think that, but no. Pretend you never saw that. That's never 0. So the only way this is going to be 0 is if this is 0. So in general, you should be able to use the quadratic formula, or in particular special cases, maybe you can factor, and in this case we can factor. And we get two possibilities for S that work, -3 and -4. Actually, I haven't proven those work. What this algebra effectively proves is if there is a value of S or two that work, it's got to be these two numbers. It doesn't actually prove those work. To actually prove those work, you technically need to confirm by substituting, e to the -3t into the differential equation. I mean, the calculations would be basically the same kind of thing, but technically the logic here is if there is a value of S, or more than one value of S that work, then S must be -3 or -4. You should be able to check it, but I'm not going to require you to. Okay? So e to the -3t and e to the -4t evidently are solutions. And it turns out that the general solution for this second order scalar equation is an arbitrary linear combination of e to the -3t and e to the -4t, meaning take an arbitrary constant, call it k1 times e to the -3t, plus another arbitrary constant, call it k2 times e to the -4t. With second order equations, you need two arbitrary constants, and to solve initial value problems, you need two initial conditions. Let's go ahead and assume I've got a couple of initial conditions. Say y of 0 is 1 and y prime of 0 is 0. That's the simplest kind of case and maybe most typical. You let the mass go from rest, making the initial velocity 0. Plug in those things in here, use this one to say 1 equals k1 e to the 0 plus k2 e to the 0. It's k1 plus k2. To use the second initial condition for the initial velocity, I'd have to differentiate the function. I'd have to find the velocity. I'll go ahead and call it v here in anticipation of our next topic today. V is the velocity, that's the derivative of the position, which by the chain rule is -3k1 e to the -3t minus 4k2 e to the -4t. And the fact that y prime of 0 is 0 now implies 0 equals -3k1 e to the 0, which is 1, minus 4k2 e to the 0, which is also 1. And your system of algebra equations to solve for k1 and k2 now includes that one and this one. And that'll give you a unique solution to the initial value problem. Let's see, this one will imply that k2 is -3/4 k1. I'm doing this now by substitution. Right? K2 is -3/4 k1. You can then substitute that into this other one in place of the k2. So So you get 1 equals K1 minus 3/4 K1, which is 1/4 K1. It looks like K1 is 4, which would then make K2 equal to negative 3. And the unique solution of the initial value problem then would be 4 e to the negative 3t minus 3 e to the negative 4t. Is that right? I believe so. That would be the unique solution to the initial value problem, if I haven't made any mistakes. Does it look good to people? As you already have read about and done problems related to this, you should be able to convert this single second order equation, second order scalar differential equation, into a first order system of equations. This is something we do quite often in this class. The reason we do it is because we want to think about phase planes still. And ultimately, even use Euler's method, though Euler's method is not needed for this example, in a two-dimensional setting. Use Euler's method in a two-dimensional setting. So what do? You let v be the velocity. In other words, v be y prime. And that definition becomes one of the differential equations in your system. You can also write dy dt. That is one of the equations in your system. The other equation comes from this, comes from the fact that y double prime is v prime. Those are both ways to represent the acceleration. And y double prime can be written in terms of y and y prime by solving the original differential equation for y double prime. Negative 12y minus 7y prime, or negative 12y minus 7v. It's a prime here, not a 1. So your system, your first order system, first order because it only involves first derivatives, is dy dt equals v and dv dt equals, get the order right, it technically doesn't matter as far as whether it's a good equation or not. However, it'll matter for using matrix methods in chapter 3 to get the order right in the second equation, to put the y term first and the v term second. Because the y equation is first and the v equation is second. That's why. Write negative 12y minus 7v. It would be okay, again, technically, to write negative 7v minus 12y. However, it's a bad idea because when we use matrix methods in chapter 3, we will want the orders to be consistent. Y then be here, y then be there. Let's use Mathematica to solve both of these things. And we'll go ahead and use DSolveValue. DSolveValue. These are linear equations, and DSolve and DSolveValue have no problems with those. I don't need to use NDSolveValue. You can type it in. The original equation is a second order equation. Y double prime of t plus 7y prime of t plus 12y of t equals 0. I'll put my initial conditions in. Y of 0 equals 1. I do have to type y prime of 0 here instead of v of 0 because in this code, Mathematica wouldn't know what v is. Equals 0. Solve for y as a function of t. Okay, that wrote the answer as a pure function. To avoid seeing it as a pure function, Put a y of t there. There we go. And again, for some strange reason, it doesn't expand. There we go. That's what we got by hand. Yep. The first order system with analogous initial conditions should give us the same answer, although it'll give us the answer as an ordered pair, y comma v. As a first order system, your equations are y prime of t equals v of t, comma v prime of t equals, what was it, negative 12y, don't forget your t's, minus 7b, don't forget your t. Here we need a v instead of a y prime. I'm not just solving for y, I'm also solving for v. That's the same answer, but in vector form. As a list in Mathematica, the first entry is y, that matches that. The second entry is v, the velocity, it's a y prime. Differentiate this, you get 12 e to the negative 14 minus 12 e to the negative 3t. That's y, that's v. You can sketch the graph of this as a parametric curve in a phase plane. What's the vector field? I should probably call the vector field, well, I'll call it G again still, but I should call its inputs y and v instead of x and y. And don't let it confuse you. The horizontal axis here is going to be a y-axis, because y comes first. And the vertical axis is going to be a v-axis. The velocity, v, comes second. So it's a little confusing that way. I'm defining the vector field. What is the vector field? It comes from the right-hand sides of the differential equation. Those right-hand sides I can represent as a vector field. G of yv equals v for the first component, negative 12y minus 7v for the second component. That's what I have to plug in for G. V for the first component, negative 12y minus 7v for the second. Change the x and y to a y and v. Mostly to avoid confusion here of what this is all representing. I've got formulas here. I don't need NDSolve. I don't need these things. Just copy and paste this into the parametric plot right here. Where's our solution curve? There it is, like that. What does it mean as far as the mass in a spring? It means if we start y out at 1, if we pull, let's say the spring is going back and forth this time, if we pull the spring 1 meter from its equilibrium position and let go, the initial velocity is 0. This point is 1 comma 0. Y is 1, v is 0. And initially, the position doesn't change very much. It starts moving toward the left because y is becoming smaller ever so slightly. But the velocity is becoming negative because the mass is moving to the left. And in fact, the velocity stays negative, y decreases, the mass heads toward its equilibrium position without oscillating. The damping is sufficient that we don't get any oscillation, we don't get any spiral sink behavior. You got to interpret this picture correctly. This is not a picture of the motion. The mass doesn't go down and up. This is a picture of showing you what the y and v values are over time. What's the position, the displacement from equilibrium, And what's the velocity as time goes by? This curve, the solution curve, keeps track of those values. That's what it's doing. But you can think about what's happening with the mass. I let the mass go. It speeds up because the velocity becomes more and more negative for a bit, then it slows down as it approaches the equilibrium, and the damping is so great that it never oscillates. It just slowly heads toward y equals 0, b equals 0. That's the motion. So you gotta make sure you're careful to think about that every time. It's real important that you do that. This is called the phase plane, the YV phase plane. So we just did this converting for this example. We also could write the differential equation in vector form, by the way. If we combine these two things, and if we let capital Y be a vector whose components are little y and little v, we could write the differential equation in vector form most compactly like this. dy dt represents a vector whose components are dy dt, d little y dt and dv dt, and g of y represents a vector field, this vector field right there. Okay, these do take some getting used to, but once you get used to it, it's not too bad. All right, let's spend a couple minutes with what I call fully decoupled and partially decoupled linear systems. This is not related to masses on springs necessarily. In fact, mass on springs really doesn't quite fit this scheme here. A fully decoupled linear system is a system of first order equations where the dx dt equation is a linear function of y on the right hand side, like 5x, and the dy dt equation is a linear function of y on the right hand side, like negative 3y. It's very easy to solve such systems like this. They're fully decoupled because this equation doesn't involve y on the right hand side, and this equation doesn't involve x. It's like they're two separate equations that I can think about separately and solve each separately and then just put the answers together. The general solution, if I write it in column vector form, would be an arbitrary constant times e to the 5t for the x component, and an arbitrary constant times e to the negative 3t for the y component. Because you just think about each equation separately to get these two functions, and then put them together in a vector to get the general solution of the system. So fully decoupled like this are pretty easy to solve. Give me 1 minute just to talk briefly without fully solving it about partially decoupled. Partially decoupled linear systems. That's where one of the equations only involves that one dependent variable, but the other one might involve the other one. For example, if dx dt was 5x minus 7y and dy dt was negative 6y, that's a partially decoupled system. The dy dt equation has no x's on the right-hand side. However, there's some coupling going on up here. The dx dt equation has y on the right-hand side. This is harder than this, but not a ton harder. You can, for example, solve for y here. And you call its general solution k2 e to the negative 6t. You can't guess what the answer is for x right away, but you can substitute this back into this equation in place of the y and get a non-homogeneous linear equation that you can solve either with the method of undetermined coefficients or with integrating factors. I won't take the time to do that because we're out of time. Book's got examples. Make sure you study those. The homework completion assignment due on Friday, or excuse me, on Friday, involves problems from 2 sections. Okay, they're both fairly short sections. All right, see you then.